Going to talk about two wonderful techniques, cross-validation and bootstrap, and these two techniques are within the realm of resampling methods, and we are going to see when to use which one of these methods. It's a very interesting topic because it can be applied in almost all situations, and it has a lot of applications. So these methods have two main applications. The first application for cross-validation is to use what type of flexibility we use and how much our test error is if you do not want to waste a lot of data of yours. And bootstrap is used to estimate the standard error of your parameters. And that's the second thing it does. And if you have a situation where you cannot find closed-loop solutions for your parameters standard error, you use bootstraps. So with that introduction, let's see what these are doing. Okay, so let's look at some easy examples. Let's have a recap of what we had earlier. When we want to find the correct flexibility in our samples for models, let's say for example we want to decide what degree of polynomial we use for our data, what we usually use is test error. So we divide our data into two sets and then look at how much error our test set is making based on the training data we use to train our model, and we use the minimum test error that we can achieve from it. One of the problems of using training error as a characteristic or as a criterion to decide how well we are doing is that it dramatically underestimates the error. Why? Because if you use more flexibility, it goes after individual observations, and that drastically underestimates the total error that exists if we were playing God and we knew the real underlying functional form that would define the association or relationship of our response and independent variables. So here that's a two-dimensional picture. So if that was the true one, and if we were using a more complex polynomial to decide that would dramatically underestimate it, because it would go after all individual observation. It will go after irreducible error that we should refrain from. So usually we work on test error instead, and test error usually is minimized at some place. Our training error will always decrease if we use more flexible functions. So if we increase the flexibility of our models, the training error always decreases. However, the test error has a minimum all the time, and that's because after some point when you overfit your data here, the training data, the test data that has not shown to your model tend to have more errors. So it's minimized error. So that's the base of using test sample and to decide whether we are doing good or not in our prediction. So one of the there's some issues that try to use there's some methods that try to solely focus on training data and its flexibility and try to adjust it based on flexibility. Try to adjust the training error based on flexibility so that if you add more flexibility, it adjusts the training so that we do not overfeed our data. We do not get into the the problem of overfitting data by adjusting based on flexibility. So the more flexibility goes, the adjustment terms kicks in for the error you get in training. Some of the models that are going to use CP statistic, AIC, and BIC. You will see it in later lectures here, so I'm not going to spend any time there. Another method we can use to estimate the test error is using holding outset or a subset that is not being seen by your model, which is called the test error. So let's focus on that. So let's focus on the easiest way to divide our training and test data, and that's called validation set. In validation set, you basically divide your data into two parts, the training and test error. So half of your data would be seen by your training set, half of it would not be seen. And the set that is left aside is called a validation set, holdout set, or test set. So you fit your model based on your training set, and then you see how well it does on the test set. And based on that, you just measure the MSE of your test set and you use that as a proxy to the real error you make. This is a schematic representation of what I just told you now. Here we have half of our data, which is split to test error, training error, and training set, and half of it, which is assigned to our test set. So it is literally split in two halves, and then we train it based on this training set, and we test it on this test set. So one of the things that is interesting to realize is that there are many different ways to divide this whole data set from 1 through n into two training and test set. For example, you can consider first half of it. So if I want to divide this data set, I can assign this part to training and this part to test, or vice versa, or I can assign every other observation to training set, so that's these observations, and every other to test set. Or I can randomly pick half of them as training and half of them as test. So there are actually many different ways to do that. I think that's in the order of 2 to the power of n minus 1, I think. That we can do that. So, because basically you want to choose half of the n's from a sample size of n. I think it will be in the order of 2 to the power of n minus 1. I have to double check that. Do not take my words for granted. Just see how many ways it can be done. But if you have a large data set, there are millions of ways to do that, billions of ways to do that. So here is an example of 392 observations, which are split into two sets. A training set, which contains half of the data, and half of the data is 196. 392 over 2 is 196. And half of the data, which is treated as test set, is 196 sets. So here we can see what will happen to the average, what happens to one case of this split if we try different polynomials on that. For example, we just start with the simplest polynomial we know, which is a line. Here we use training error, training set. I don't know why I repeat training set as training error. I don't know why it does it, but why you do it. So basically you just input training set here. You estimate beta hat 0, 1 and beta hat 1. And once you do that, you just put test set inside it, estimate y hats, and see how well you're doing for this case. So this is the error you get from polynomial degree 1. You do the same thing for polynomial degree 2, for example. You introduce your test set, training set to this model. You estimate betas. Then you put inside the test set you have and estimate y hats. So you do it over and over again and find MSE for each case. And as for one instance, we can see this is the case we get. We can see that our test error decreased from a simple line to second degree polynomial, and then it's pretty flat. So if I were you, I would just choose the polynomial degree 2 as my model, basically because if you choose a higher degree of polynomial like 8, the problem is when you just build up your confidence intervals around your lines, you will get a waggy tail at the end of these observations, at the range of these observations, which are the beginning of the observation and the end. So the mean and max of our observations see a very huge and large and unbelievably bad confidence interval. So it's better to stick to the small one. If you just see very small improvement when you increase polynomial degree of polynomial, just to stick to the easiest one. The simpler, the better. That's our first rule. So as I said earlier, we can just do that experiment with many different training and test sets, because we can split our data into two or in halves in many different ways. There are billions of ways to do that. So if we do it over and over again, we get different test error sets for different degrees of polynomial. So this is one instance, this is another instance, and so on and so forth. All of them have the same, they're all minimized the same place, so they did pretty good job in finding where what is the optimal level. But as you can see, there is so much variability, so we cannot use it as an estimate for our real test error, because depending on which model we use, we see so much difference. So, when we use validation, simple validation method, where you just split your data in two, you can see so much variability in your validation sets. That's the problem. You show so much bias, better say, in your test errors that you get. Depending on which set you use, you see different test errors. And it tends to overestimate the error. Can you say why? You probably guessed it, and the reason is we just use half of our data as training, and usually the error you get has a reciprocal relationship with n. If the standard error of your error usually have this relation with number of observations you have. So since your training set has only observed half of the real data, it tends to make around 40% more error. Where did I get that 40%? Square root of, so your total observations is n over 2 is 2, so square root of 2 is 1.41. So without changing anything, just because of the fact you have lower observation in training than your real data set, you're making 40% more error. So as we saw, the validation, which was basically splitting our data into two sets, wasn't the best method we could use. We saw so much bias in our observations, in our predictions. We saw that we are overestimating our error. That's why we use some new method, which is called K-fold cross-validation. So in K-fold cross-validation, I think it's better that I go to somewhere that I can draw something for you. So let's say you're interested in fivefold cross-validation. In fivefold cross-validation, you just split your data into five different partitions. You can do it in any way. So you assign one part as test, the rest as training. So you train your data based on your training. O stands for training here. X is test set. So you assign 4 parts as training, 1 part as test, and you just estimate the error you get from this model. Let's call it error test 1. You do the same thing with the next partition. So you're considering 4 of these partitions as inputs and 1 as test, and you estimate how much test it creates, test 2. You do it 3 more times, and each time you're assigning one new partition as test, the rest as training. So here we have OOXOO, we have OOOXO, and lastly OOOOX. So we get training error 3, test error 3, test error 4, test error 5. So our total error would be just the weighted average of these tests. So that is fivefold cross-validation. If it was tenfold, we would just divide our data into 10 different sets and do that training and testing thing 10 times. So we basically divide our data into k parts. We use k minus parts as training. We try that on the test set, that test part that is set aside, and we do that k times for different partitions. And lastly, we just combine the results to get what we have. And here's a schematic one. We have 4 parts of training. This do not let this triangular shape, rectangular shape deceive you, because I think validation couldn't be fit in this rectangular shape. That's why it's bigger, but it should be at the same size as 2, 3, and 4, or 5. So you set aside one validation, the rest training, and you just change your validation to the second partition, third partition, fourth partition, fifth partition, and every time you just estimate your test error, and you do that, and finally you get the total error, the average error you make. And the way you estimate CVK, or cross-validation of k-fold validation, is this formula. So do not let formulas scare you. It's actually very easy to think about it. Since okay, so let me get back to my original case. So let's assume we had 99 observations. Is it any way that we can just divide these data into 5 exactly equal partitions? No, because 99 is not divisible by 5. You cannot divide it by 5. So as a result, you get one set of X that has 19 observations, and one set that has 20, and the rest will have 20 as well. So what that formula is trying to say is that you take a weighted average of the MSE of the trainings you get. So let's work on it. So for example, so that TE1 is just basically MSE1. So basically TE5 is MSE5. So what that says is that the cross-validation error you make for fivefold cross-validation is the weighted average of these MSEs. So that's 19 over 99 MSE1 plus 20 over 99 MSE1, MSE2 plus 20 over 99 MSE5. So we find the error, and based on that, we can just have the total cross-validation you make in any flexibility level. One of the other things we can do is to split our data into exactly the same number of observations we have, n observations. So that will be n-fold cross-validation, and in a sense, this is leave one out, because if, let's say, these are our observations, if you just assign this as training, the rest will be, assign this as test, the rest will be training, and then next time you assign this as test, the rest will be training, and so on and so forth. So that's n-fold cross-validation. The n-fold cross-validation has another name, leave one out cross-validation. So there are 3 famous k-fold cross-validation: 5-fold cross-validation, 10-fold cross-validation, and leave one out cross-validation. So as you can see, the leave one out cross-validation has the most computation part, because we have to repeat test and training n times. In 5-fold cross-validation, we would only try that 5 times. In 10-fold, 10 times. But in leave one out cross-validation, we have to do it n times, and that's a very large number. So basically, computationally speaking, unless we use a shortcut that I show you in the next slide, leave one out cross-validation tend to take longer. But fortunately for linear regression lines, we can use a shortcut. And the shortcut is you just run your linear regression line once. You just run it once. So you just run it once on all of your data, and then you adjust the error you make this way. So this is, so let's assume these are our data points. So let's call this one x1. So the estimate of x1, which is y1, y hat 1 is this, right? So on the line. So the difference of these two is the error we make. So if we would sum up the squares of that and divide it by total number of that, we would get the MSE. But here we adjust that by the influence it had on the regression line. And the influence it had comes from the diagonal of the hat matrix. And it shows how much leverage it had on your regression line. And H's are usually between 0 and 1. It has a lot of leverage. If it was a high influential point like this or this, it will be closer to 1. If it's not, it's closer to 0. So it will adjust it based on the weight that influential point had on this regression line. So just for linear regression lines, it's extremely easy to find cross-validation of leave one out. You just need to run your regression lines one time, and these H's are easy to compute, and it always comes with in many standard packages, including R. You can find HIs there. So you just need to run it once and you can get that instead of running it n times. One of the problems of using leave one out cross-validation is that. So in any k-fold cross-validation, remember leave one out was just n-fold cross-validation. When k goes up, variance goes up, bias goes down. So there is a trade-off between variance and bias. So for n-fold cross-validation, which k is the largest amount it could be, the bias is very low, but the variance is high. We should use we should use a k-fold that is optimal, has a good balance of variance and bias, and that's why in practice usually k is 5 or 10. I have seen more 10s than 5s, to be honest with you, but this is the most practical values that you can choose. And here is an example. So this is the test cross-validation error you get from leave one out cross-validation. It is minimized again at 2. It is minimized here, but as I told you earlier, it's better to stick to the simplest one. Here we did 10-fold cross-validation, and actually not me, the authors of the book did 10-fold cross-validation with many different sets. So again, you can partition your data into 10 folds in many different ways. So they did it in many different ways. And as you can see, the results they got are so similar. In validation, where we only had 2 sets, we saw a huge difference between the 2 curves. But in 10-fold cross-validation, they're very close. So again, it shows that 10-fold from the bias point of view is very close to leave one out cross-validation and has low variance. And here is simulated data. This is the test error you would get from real data that will minimize this flexibility. The dashed line here represents leave one out cross-validation, and the orange one represents the 10-fold cross-validation. So in this case, as you can see, they found a minimum very close to reality. And here's another example. It's again very close. If you would dismiss the flatness here, you would pick the correct flexibility. So here and so here, they did a pretty good job here. So it shows how cross-validation works in real life. So So one of the issues here is that since our training set only works with k minus 1 over k percent of our variables, or portion of our total data, again, our prediction error we get is usually biased upward, because your data didn't see all the data points. If it would, the error you would get would be less. The next thing is bias is minimized. I think I explained it earlier. Since n is large, the bias is the smallest here, but the variance is high. K5 of 10 has a balanced bias variance. And the next key thing is we can use cross-validation for classification problems as well. It's actually pretty simple to deal with that. And again, do not let this formula, in addition to this one, scare you. It's actually very easy. I give you a numerical example in a couple of seconds. So I want you to write this down somewhere and just if you haven't written it down yet, just pause it, and well, once you're done with it, just come to the next slide. Okay, so we want to apply the formula for error for cross-validation in categorical variables. So let's say we had 99. Sorry, that is okay. We had 99. We were working with fivefold cross-validation. And we have 99 observations. Again, 99 is not divisible by 5. That's why one of our categories will only have 19 observations in it. So that's, for the sake of simplicity, just let's fix the first category as 19. First partition as the first partition as 19. So this will have 19 observations, 20, 20. So I'm talking about the test part, 20 and 20. So let's assume in that 19 case, so you train it based on these 80 observations that are left, and then you use it for prediction. You find that 2 out of 19 you misclassified it, 17 was okay. In 20 you find 3 misclassified, 17 were okay. The next one, 5 were misclassified, 15 were okay. 4 misclassified, 16 were okay, and lastly 1 misclassified, 19 were okay. So the formula simply says, let's take the weighted average. Let's take the weighted average of the errors that are there, and errors are simply the times that you misclassified it. So that would be, so the 19 over 99 is the weight of this observation and total observations times our misclassification error is 2 out of 19 plus 20 out of 99 times 399, and you do that up to the case you get to the last one, which is 20 out of 99 times 1 over 20. So one great thing about it is we just canceled that was 3 out of that was actually 20, not 99. So 20 will be canceled by that, and 19 will be canceled by that. So what you will be left with is just total number of misclassification errors you've made divided by 99. So the total misclassification error here is 15 divided by 99. So it's nothing fancy. We can also estimate the standard error of that. This is a naive way to do that, by the way. It's not the true standard error you get, but it's a very useful value. The reason I say it's not a correct standard error we can get is because these errors are correlated with each other. Our training sets, so let's focus on the first training set and the second training set. So as you can see in the first training set, second training set, 3/4 of our observations are identical. So our observations are no longer independent. And that's the problem, that we cannot use standard error here as a good proxy. But that's the only thing we can do, so we stick to the standard error we get from here. So we learned how to deal with cross-validations. Now let's see what is wrong if we misuse cross-validation methods. That's a very important topic, and you can see it you can see that this problem has been identified in a lot of research that have been even recently published in very good journals. So that's a very important topic, and I want your full attention here. So let's say you have 5,000 predictors and 50 samples. So your predictors are so much more than your samples. So you might be tempted to pre-screen the data. So what you do is just you use correlation between your outputs and your predictors, and handpick the best 100 predictors, and then you use cross-validation to see how much test error you make. And then you get very happy, because usually it's very easy to get very good results even for random reasons, and you say, okay, that's the best. So that's a terrible thing to do, because when you do pre-screening, your training set has already seen the predictors, so you just cheated. In cross-validation, you set aside a set that hasn't seen the predictors, and based on that, you decide how well you're doing. But if you do pre-screening like that, you're cheating. You show that to your training set again at the beginning, and when you show it to the training set at the beginning, all of your data have seen the predictors. So if you do a simple correlation analysis, your training data has already seen, all of your data has already seen the predictors. So you choose the best predictors that you can find, and then when you do cross-validation, there's not a blind test anymore. So it's very easy to show, even if you just create random numbers. Let's say simulate. So to do this practice, you know how to use it. Use R. So let's say this is my outcome, and this comes from a simulation of I don't know, 1,000 observations of flipping coins. When it's head, it's 1. When it's tail, it's 0. So then, for let's say 1 million times, simply simulate flipping a coin. So I assume a friend of yours is flipping a coin, another friend of yours is flipping a coin, and so on and so forth. Then only handpick or cherry pick the few variables that are highly correlated with this one. So I think you agree with me that the way I flip the coin should have nothing to do with your friends, because they're independent events. But if you cherry pick them and then you use cross-validation, you get very stupid results. You get almost 0% test error. So that's extremely important. So you cannot do cross-validation if you have first step, which was screening. You can do screening. You can do screening in a correct way. So the wrong way of screening is that use all of your predictors and everything that you have here to pick a subset of predictors and then use the crossvalidation. That is the wrong way to do that. A correct way is to, from the beginning, set aside your test set. So all of your outputs and all of your inputs are set aside. So then you can do the screening inside what is left. Now you can do the pre-screening. That is totally fine here. And then you can do any pre-screening method you want. You may want to choose some predictors, but when these predictors are shown to the test set, it hasn't seen it. It is not trained upon it. So that's a very important thing to remember. If you do not take these steps correctly, you may get some nonsense results, and you might get carried away, and it's not good. So the next topic would be bootstrap. We're going to talk about it in our next lecture. Thank you very much.